Tēnā koutou katoa. Welcome to the first parallel session in the Green Room. Gives me great pleasure to introduce Mark Gahegan, the Director of the Centre for E-Research at the University of Auckland. Mark's the inaugural Director of the Centre and a Professor in the Department of Computer Science. Prior to that, he was the Associate Director of the GeoVista Centre at Penn State. He's got a list of publications and talks and various funded research projects longer than both my arms and both my legs. He's on the board of a number of journals and is very involved in the setup of the national e-science infrastructure here in New Zealand. So put your hands together for Mark.
Thank you so much, Sam. I'm going to wander around a bit. I've got a mic on. If you can't hear me, just put your hand up. But I think the sound guy's got us all under control. So thanks for coming to listen. As Sam said, I'm a researcher. I sort of dabble in IT from an institutional point of view, but I am a researcher at heart, and I wanted to talk a little bit about what the data revolution means to researchers and how it's changing the nature of the research questions that we ask, and I want to give you some examples of that. So in this brave new world, as you'll see, many of the talks related to the research sector in universities over the next few days are around research data. And every research institution is struggling with how do we manage this, how do we provision the storage, how do we educate researchers, how do we organize the data so it becomes an asset and not a burden. I'm assuming that we've already done that because I want to talk about what comes next. For a researcher, the goal isn't tidy research infrastructure at the institutional level with metadata federated amongst all the catalogues. That's not what researchers care about. Sure, they care about data discovery and people being able to utilize their data. But what they really care about is using the data in new and interesting ways. And I want to talk a little bit about that. To do that, I want to talk about three specific questions. So again, this is going beyond managing research data at an institutional level and towards what do researchers want to do with the data now that it's well managed. So let's assume that it is well managed to begin with. I want to give you three specific examples of where this ubiquity of data is really changing the way research works. The first is that data is helping researchers move from analytics and simulation to discovery. And that's a big step. You've probably heard something of who's heard of the fourth paradigm? Could you put your hand up if you've heard of the fourth paradigm? So the fourth paradigm is all about can data drive discovery? And I want to give you some examples of how it actually does, how it is driving discovery. The second is how we describe research data so that it can be reused. And I'm doing this because I want to show you that this is actually an open question. Researchers don't know how to describe their data so that it can be most effectively reused. It is an open question. And I want to give you some examples of the ways that it could be described and perhaps challenge you to think beyond just subject-level metadata. And the third is actually about copyright and licensing, and encourage you to look at how licensing and copyright can change the ecosystem from being sterile and unproductive to being very productive and encouraging the reuse of data, and how licensing actually might change the effectiveness of a research community. First of all, data is changing the research paradigm. Those of you who know about the fourth paradigm, and there's a great book by Jim Gray et al. About what the fourth paradigm is. It's called the fourth paradigm. It's available free from Microsoft. You can get a PDF of it from Microsoft. It talks about how data has the capability for changing the way we do research. And the book talks about 4 paradigms in the history of research, starting with the experimental paradigm, where we measure the pendulum swinging and we increase the length of the string, or we increase the heaviness of the weight, and we monitor by keeping one variable, changing one variable and keeping other variables constant, how the system responds. Through to the theory-based paradigm, or the analytical paradigm, which you could think of as being headed by folks like Einstein, who proposed a way of thinking about science by approaching it theory first. Einstein's discovery of special relativity, his first major breakthrough, wasn't actually proved, or wasn't actually established with any evidence until 50 years or more after he proposed it. It took 50 years for us to gather the data that would help see whether that theory was a useful theory or not. Turns out it is. The third paradigm, which is where IT started to make a huge impact on research, is in the area of simulation and modeling. And you see that going on now in pretty much every major science and engineering discipline, and more and more into the humanities and into the fine arts too, and the social sciences. And it's the paradigm that says, well, we can simulate and analyze using massive computational resources, and that's changed the way many sciences operate, from forecasting climate change through to nanomaterials, through to genomics and bioinformatics. And those paradigms have had a phenomenal impact on science. And all of the e-research centers, or e-science, or cyber infrastructure that you see around the world as a result of that third paradigm of science, the moving from the hard world of the lab to the digital or virtual world in order to do science. Moving science so it is digital. The numerical simulation, or the third paradigm. But the fourth paradigm goes further. And it says, well, in the past, theory came from humans, or theory came from observation. Theory came out of simulation. What if theory could come by learning from data, by induction, learning about patterns, or even inducing entire models for how systems behave from the data? Could that ever happen? Well, yes, it can. I want to give you a couple of examples of things that we're doing at the Centre for E-Research at the University of Auckland that help make that case. But you'll probably have good examples of your own. The first is in the area of deep learning, which is, I know, a buzzword, but I want to show you a few of the things that can be done in that area. The second is even more of a stretch, and it's in an area called computational model discovery. It's a brand new area, and learning about that might be new to some of you. But the first is a project that we have in collaboration with the University of Otago, and it's a thing called KidsCam. And in KidsCam, 169 kids, about 12 or 13 years old, around the Wellington area in New Zealand, have been persuaded, ethically, to wear these little devices around their necks that take a photograph and capture a GPS measurement position every 15 seconds during the day, while they're at school and while they're at home. Oops. That means that we've captured 1.3 million images, and we've got GPS records of where children were with this little device called an autographer. These images have to be manually annotated by researchers so that they can find out what's happening to children. The things that the researchers are interested in are things like food exposure and consumption, particularly fast food and sugar, computer use, alcohol and gambling, marketing, and how much children are exposed to those things. These are really important research questions. But the question the researchers came to us with is, could all this be automated? The cost of having to digitize all of those frames of video by hand is enormous. And the people who have to do it are the poor postgraduate students who work for the important professors in the labs. They sit there annotating thousands of images. Oh, there's a fizzy drink in this image. Oh, there's a gambling logo in that image. Oh, look, the child's still on Facebook in this image here. And we do that, and then we can calculate exposure. But what if we could use deep learning to do some of that for us? It can be automated. Deep learning is the state of the art in image recognition. It uses deep neural networks. Neural networks have been around since the 1970s, but quite recently, a particular brand of neural network has emerged that can not only learn a task, learn how to classify imagery, but it can also learn how to configure itself to best solve the task as it solves the task, which means the researcher doesn't have to do that. The big problem with neural networks and many other machine learning tools is the huge learning curve the researcher has to go through in order to use them effectively. They have to learn how to train them because these things are delicate. And once they are trained, they typically only work on one data set, and training them is a mammoth task for the uninitiated. But what if the system could learn how to train itself as well as training itself? And it turns out you can. So these are large artificial neural networks. Usually they're running on GPU devices. If you give them labeled examples from experts, so instead of having to label all of the images in your data set, we only have to label a fraction of them, 1%, maybe 5%. Can you then use those labeled images to train a neural network to find the rest of them and save everyone a lot of time? And can you, while you do that, find out the accuracy by which you could do that training so you know how much to rely on the results that you generate? So you can measure accuracy and sensitivity. There are a number of toolkits around for this kind of thing. We found NVIDIA digits to be quite useful. But Google and Facebook also have open source technologies you can use for this. And many researchers are starting to become interested. Here's an example of a frame from that autographer camera captured in a classroom. We've blanked out the kids' faces there because we're not supposed to show that in public. The system can even learn to do that for you. But you can see right in the middle of that table, product placement, right in the middle of the school, sugary drink. Those kinds of things are really bad for kids. They have about 27 teaspoons of sugar in them. And apart from rotting their teeth, they make their kids hyperactive and they put on weight and they get all kinds of health problems later in life. We would like to minimize their use by children, and certainly within schools. You can also see there's a slightly more healthy-looking snack there on the table as well. What we would like the neural network to be able to tell us is that's a classroom, and, oh dear, there's a sugary drink in the middle of the classroom. How well can we do that? Well, here are some examples. I could give a lot, but I don't have a lot of time. These are predictions made by that neural network, the deep learning environment, having been trained on a few thousand images. And it's predicted quite correctly that this, on top left there, is a snack food. It's pretty much 100% confident about that. And it's predicted on the second one down there that that's a sugary drink. Again, it's very confident with that prediction. Have a look at the sugary drink in particular, and you'll see that the logo is completely obscured. There's no way that you could tell that that was Coca-Cola, for example. There's no branding available, visible in that scene, but the network has learned that that kind of a bottle with that kind of a label, that kind of a color, is most likely to be a sugary drink. And it's done that because we've trained it on thousands of examples using different poses, so that the network learns with high confidence to predict these things, even if they're partly obscured. This technique actually works. You need more learning examples than perhaps we would like, and you need to be really careful in the way you set up your problem so that what you hope to see as a result of doing deep learning is what the neural networks can be trained to disambiguate well. The neural network can't be trained to disambiguate fizzy drinks or sugary drinks well, but it can be trained to learn to recognize Sprite and Cola and all of those other brand names. It's really good at specific stuff. So you train it on the specifics and then you generalize. So this stuff works. And it means that researchers who face the problem of having far too much data to analyze and annotate can now rely on discovery systems and deep learning systems to help them over that massive hurdle, and they can do more work more quickly with less cost. Here's a second outcome. This is a map of where children have gone. But we've also found that we can make maps of what children are exposed to in the environment too. And that's a game changer. We could now make a map of an environment that shows where children are most exposed to gambling or fizzy drinks or fast food. That's a really interesting idea. A map of a surface in an environment that shows where children are more at risk, for example. The second example is even more compelling than the first, I think, and it's to do with computational model discovery. This is the dream of the fourth paradigm. Could you actually learn a model from data without any theory that describes how something works, not just in the language of neural networks, which no researcher could understand, but could you express this model in the language of theory, the theory that a researcher would use to describe the model for themselves? So what you want is a model that works in the language of the mathematics that a researcher would use. A common example in ecology is the predator-prey relationship between lions and zebras. And you can see predator and prey there, and when you have too many prey, you get more lions, and when the prey is all eaten up, then the lions get hungry and they start to thin out too. So you get this relationship between these two populations. Could that be discovered just by looking at those two graphs? And this is quite a new area of computing. Very few researchers are working in it, but it is actually true. It can be done. There's a process now called model learning that can happen using similar kind of inductive techniques as neural networks use. Instead of giving it small patterns to learn, you start training it on mathematical formulae, small pieces of mathematical equations, and constants, and relationships that are common in a particular field. You then, by providing it with enough data, give it the opportunity to learn how to describe relationships that fit the patterns in that data. These relationships, these formula here, were actually created by a learning environment. They were derived from the data. So in other words, given enough rich data about how a system behaves, it's possible to learn from it. Formulae that can be learned in classrooms, that can be understood by researchers, that can be tested for their validity in terms of understood domain theory and domain constraints and current domain knowledge. This is a game changer. Systems that can discover relationships in data and describe them in a theoretical way that can be communicated to researchers. They might discover something that we, clever researchers, clever as we are, hadn't thought of yet, or had misunderstood, or simply hadn't had the data to pursue. In an environment where all data, all experimental data, is available and marked up and discoverable, systems could be put in place that simply went from repository to repository, looking for correlations in data sets, and then trying to express them in domain theory, and then trying to get researchers to look at that domain theory and see if there's anything in that. Is that a meaningful relationship? So you could see computational model discovery tools used as partners by researchers to help them find out things that they didn't know before, or perhaps suggest avenues of research that where no one's looked yet at possible correlations. This is a game changer. I want to look very, very briefly at a few other things. I talked about research data, and the challenge here is to move beyond the way we think currently about how we'll describe data from an IT point of view. How do I describe data as an institution or as a researcher who makes that? As an institution, we typically want to describe data in an institutional repository using a subject index. That's not going to help a person who wants to use the data for the first time. So instead, we should be thinking, what kind of data descriptions are demonstrably useful to researchers to help facilitate reuse of data? How could we describe research data? Well, we could describe it using some kind of descriptive institutional metadata. We could use tagging, tag clouds, or some kind of easy-to-impose sort of frequency-based metrics. We could use deep semantics to annotate data, particularly if it's text-based. We could look at the community of people who made the data and the community of people who use the data, a kind of friend of a friend way of looking at a data set. Knowing how a data set is situated socially says something about what it means to different people. Or we could go the kind of Amazon.com way and build a recommender system for data. People who use this data set often use that data set too. People who were using this method found that data set was helpful with it. This has been found to be useful too in some online communities. All of these ways have been tried. We could use method or workflow to describe data. And this is a way of describing data that's become very popular recently. Describe how the data came to be. All of these ways of describing data have their own challenges. All of them are important. We don't know, the community that does research in this area, which ones are useful, the most useful to which researchers, in which communities, and when in the research process. But I'd like you to think of them all with a question mark. Could I use that? Would it help my researchers to find data or to use data effectively? We could use all of them. This graph here shows most of those measures around the concept, around the idea of a document or a data set. It shows how people and methods and reuse all contextualize a research resource and help explain what it means to a community. All of these measures, in some part, might be helpful. There isn't much time to dwell on this last one, but I'll happily talk to anyone who's interested afterwards. But licensing is another area that rears its ugly head very often. Licensing law starts on the premise that no one has any rights. Licenses don't take away rights, licenses give rights. It's important to recognize that. Without a license, you can't do anything. But licensing is too hard for researchers to deal with without help. At stake is the freedom to use the academic record, our scientific record, and that's really important to researchers. But they need help figuring out how to use licenses. When researchers combine or mash up data, which they often do, they often have to deal with the problem of taking a data set with one license and combining it with a data set with another license. It's all too common to take a data set with the license that says, you cannot share the results of anything you do with this, and combine it with a CC BY license that says, if you use this data, you must pass back to the community any derived products. So the researcher combines these two data sets, and they cancel each other out. One says you must share the results, one says you can't. That means that the researcher is stuck. They can't go on. What we need to do is to avoid putting researchers in that situation. Some communities will want to be more locked down. They'll be much more concerned about ethics and privacy. Others will be much more concerned about openness. We need apps that can help a researcher make good decisions about what data they can combine. If they do, what they can do with the data once they've combined it. Must they share it? Can they share it? Are they able to publish the results so that other people can use it? Or must they ask for permission? All of that researchers don't currently know. So open is good, but it's not good for every community. Don't assume that's what researchers might need. Creative Commons CC0 is a great place to start, but it isn't a good place to start if some of the data sets you're already working with preclude you from sharing the data back out again. We built a little app that takes you through legalistic reasoning where we programmed it with knowledge about different licenses so that when you choose licenses for data, it can tell you beforehand what responsibilities you will have if you use this license with that license, whether it's even feasible to do so. So it captures data, you put some qualifying information in, and it tells you what the legal outcomes might be. In order to support these needs, we need specialized hardware and infrastructure. I've put a list down there of what's required for each of those technologies. But the real underlying message is that you need staff, trained research enablers who are able to talk researchers through these big challenges. It's not enough simply to store data. We have to think about how researchers want to consume it, and we have to get the specialized skills and the specialized infrastructure to help researchers make this journey from just depositing my data to using it to change, to revolutionize the research process. Thanks very much for your attention. I'd be happy to take questions.
Thanks, Mark. We don't have any questions that have come in through the app, so we're open to taking questions from the audience. If you don't mind, maybe just to stand up and project and say where you're from, that would be awesome. Thanks.
My name is Mark Bailey from Australia. So I'm curious, we talk about new ways of describing data, which is fantastic, but I'm wondering whether you have any thoughts on the metrics for reuse of data or the efficacy of a data set. If you try and set a deep learning algorithm on how you best describe data or find what's most efficacious, you would need to know how useful the data turned out to be. Or,
Yeah, you would.
and for us, in trying to do shared research storage with people, measuring that reuse, measuring that metrics about what the value of the data was is almost impossible.
It is difficult, and there's been a lot of research in all of those different areas that I described, and some cyber communities have tried them out. But it is difficult to get a joined-up view of which one is best in what circumstances, where and when. The fact that we do have now portals and virtual research communities that are supported by our infrastructure means that we can run analytics on who downloads what, and even by inference which data sets are good for answering which questions, because we know which questions might be associated with which researchers or with which research groups. So we can begin to learn. What I guess I'm saying is we need to instrument our infrastructures so we can actually gather the evidence we need to answer those questions. The techniques that gather those use or those metrics about how data might be used, those techniques are there, but connecting them together and connecting them to an active research community so that we can get really good intel on what works when, that hasn't been done. So I'm suggesting that we need to do that. Because until we do, we won't know how to describe our data well. At the moment, we're just guessing. And I think those guesses might well limit us in the end, because researchers choose to use a data set or not because they think it's in their area, but because they trust the researcher who made it, or they trust the researcher who used it, or because the researchers who made it gave enough information about exactly how they made it that a researcher feels that they might trust it. I would say literally billions of dollars goes wasted every year because researchers remake or recapture data that's already out there because they either can't find it, or when they find it, they can't trust it. So it's mostly about trust and about finding it, which a subject level index doesn't help at all. Knowing that it's in bioinformatics is, well, who cares? Tell me how you made it. Tell me if I can believe it. That's what really all of those metrics are aiming for. So thanks for the question. It's right on the money.
Possibly got time for one more quick question, Catherine?
Oh, it is just a quick question too. Catherine Unsworth at Nance. You mentioned the app, the copyright licensing app. Is that openly available at all?
I should say yes, shouldn't I? Because it is. It is. The research student who did that work is a guy called Richard Hosking. He finished about a year ago, and I think we've been lax at keeping the site up. But I did put a reference in the slides, which I think you can all get at, to the paper. There is a URL in there. I'm not sure if it's working at the moment. If it's not, we probably should reinvigorate it. It is a useful app, and he tried it out in his research, but I think it probably is something that perhaps we could build together. It's not something we think we've solved. Every country has different legislation. The app is sensitive to that, but we only built in a couple of countries. But it uses defeasible reasoning to try and figure out, from a legal perspective, which are the right precedents to attach to a particular use case. So it might be something that, as a community, we could take and build together.
Excellent. Well, could I get you to put your hands together for Mark? I've forgotten to bring his gift out, but I will give it to him in a minute. So, nō reira, tēnā koutou katoa.